All right, I think we're working now. Had a little weirdness there. Um, all right, what we're doing today is beam deflection. So if we have a beam, we're going to put some kind of loads on it, and it's going to bend some way. And we want to figure out just how it does bend. How far does it bend? We would like even to know, the entire shape of this thing as it bends. So that's what we're going to do today. This is part one, so part two on Wednesday will be the same thing except from a theoretical point of view. Today we're going to take a point of view where we've already developed a lot of the equations. So there are a lot of these equations already derived, like these. Nope, not those. These equations. So that you have, I just typed in beam deflection charts into Google, and this is one of the ones that came up. So you have a lot of equations already pre-built for you for many cases, not every case, but for many cases of beams with certain kind of loads. This table has 3 cantilever beams and 4 simply supported beams in it, and then the corresponding equations with those beams. Next time we'll get into like where do these equations come from and how are they derived. So we'll do that next time. But this time I thought maybe we'd go ahead and just do some actual calculating and figure out some of these ways and methods that we might go in and figure out how far has a beam bent at a certain location along the length of the beam. So let's start really simple. Let's get this out of the way. And let's start with a cantilever beam with a single point load on the end of it. So something like, I'm just going to draw a line for our beam. So it's a beam. We're going to cantilever it. So we're going to mount it into the wall. So this is a fixed support over here. And then for our first simple one, we're going to use one of the cases that is exactly like case 1 in this chart right here. So the top row, where it's a cantilever beam with a point load at the very end of that beam. So we're going to use that exactly. We'll put some actual values in here though. Let's put 5,000 pounds. Let's put a length of 8 feet for our beam. These equations that we have here do not depend on the unit system, so you can use either metric or US units without changing the equation. There's no constants built into the equation. Well, there are, but they're not related to the units. Let's go ahead and for now use a predetermined beam. So this beam is going to come from our charts like this. So let's see if I can find that on my side. There we go. These are the S beams. So S is standard flange I-beam. Let's use the S10 by 35. That's a good average size. It's right in the middle of our chart here. So we do have 5,000 pounds at the end of an 8-foot long beam. So S10 by 35 seems like a reasonable beam. The only thing we need from here, from this chart, is the moment of inertia. The rest of this stuff is not going to be important for what beam deflection equations we're going to use. And it's important to know that these beam deflection equations might predict, I don't know, this beam could bend a foot, like the end of it bends down a foot. It might predict that. That doesn't mean the beam actually can do that. So these equations don't take into account flexural stress or anything like that. They just give you the equation assuming the beam is infinitely flexible without breaking. It doesn't have a yield strength or whatever. Then this is what it would do. But so you usually have to pair these calculations with flexural stress calculations to be sure that the beam actually can survive whatever we're causing it to bend into. Because these equations don't tell you anything about flexural stress. It just tells you, assuming the beam doesn't yield, here's what will happen. So we need our moment of inertia. There are 2 options, the XX option and the YY option. We're going to load this beam perpendicular to the XX axis. So that means the loads would be on top of this flange, basically pushing down. And S10 by 35 moment of inertia is 147. Those units are inches to the fourth. We need one other piece of information that's not in those charts, but we need to know what material this beam is. Obviously, if we're talking about deflecting, then it's going to change the amount of deflection if we make this from styrofoam versus steel. Now, these equations wouldn't really work for styrofoam because it's not ductile anyway, but we're going to make this have basically a steel modulus of elasticity of 29 times 10 to the 6 psi. So that number, you would have to know the material, go look up the material's modulus of elasticity, and use that. All right. So I think that gives us enough to get started with our beam chart. Let's say that we just want to know the maximum deflection. So let's go through what we have on this chart. We've got a diagram showing the loading. You do have to match this exactly. Sometimes you have to mentally mirror image things or whatever to make them match your case. And don't think of L as the length of the beam. It has to be paired with the idea that the point load is at the end of the beam. So if your beam is longer, then this is not going to exactly work. We're going to have to do something to it to make it work. So for now, this problem, we have to match the case exactly as it's drawn here, or mirror image it. And so this is exactly case 1. This column just shows us kind of a prediction of what the bent deflected shape is going to look like. It shows us where y max, y is the amount of deflection. It gives us an equation for that maximum deflection. Some of these tell us where it's at. So like this one, the maximum deflection is not at the end or the middle, so it tells us exactly where that is. Same thing on this one, although it doesn't tell you in the equation, it tells you over here on the diagram. So I'm not sure why they did it that way. This is the slope in radians at the end of the beam. So this beam is, sloping in some direction, and this is that angle measure, but in radians. This equation on the far right is called the equation of the elastic curve, and it is, if you were to plot this equation, which we'll do in a second, we'll put it in MathCAD and plot it. If we were to plot this, then it would give us the shape of the beam as it deflects. So right now, let's just use this maximum and do PL cubed over 3EI. Negative because we're deflecting downwards. All right, so our equation was y max. You might use delta if you like delta for deflection. This chart uses y. Negative PL cubed over 3 EI. So P is from our chart or our reference diagram. It said P was 5,000 pounds. There is a negative sign on the equation. L is 8 feet. I'm going to convert those over to inches and cube it. This is an important point to make, and I'm going to make it on another sheet of paper so that we don't have to look at it all the time. But when we're converting units that have to be raised to a power, so we have 8 feet, and we want to go to, or 8 feet, it has to be cubed, but we want it in inches. You don't want to do, well, 8 feet is 12 inches per foot, and that number is 8 times 12. Oh wow, we're in all kind of wrong recursive mode there. Let's go to regular. 8 times 12, 96 inches, and then cube it, or what well, actually that would work out. We don't want to do the conversion at the wrong time. If we did this, 8 it converted over feet times feet, cancel out, or feet in the numerator, feet in the denominator cancel out, times 12 is 96, and then cube that, then we would end up okay. Right? That's basically what I wrote down here, 8 times 12, then cubed. But if I did it the other direction, or the other order, or another order, where I just go more like this, 8 feet cubed, 8 to the third is 512, and that's feet cubed, and I want to convert it over to inches cubed. Oh, I remember the conversion is 12 inches per feet. If I do that conversion, then my units are going to be really strange over here. I've got 512 times 12, but my units are, I have inches there. One of these feet cancels with one of those, and I have feet squared. So I have 512 times 12 inch feet squared, which makes no sense for units. So when you have to convert a number and raise it to a power, make sure however you go about doing it that you also raise the conversion factor to that same power. So here I did the converting first and then raise it to the power. Or if I were doing it the other way, then I'd have to raise this thing to the third power so that my feet cubed would cancel out with the feet cubed, and I'd be left with inches cubed. Otherwise, you'll get some very strange conversions over here, and some weird units that don't make any sense. So make sure when you're converting numbers, feet to inches or whatever it might be, and you have to raise them to a power, that you also raise the conversion factor. All right, so hopefully you already knew that, but now you have seen it again. This is an equal sign. 3. E is the modulus of elasticity. I said this thing, I didn't tell you what kind of steel. It's just structural steel, that generic steel that's in our book. So 29 times 10 to the 6 psi. And I, this was a S10 by 35. And we said that for an S10 by 35, moment of inertia was 147 inches to the fourth. So there we can solve that equation. Let's do the denominator. 3 times 29 million times 147. And then 5,000, that's a giant number. 5,000 times 8 times 12 cubed. Then divide by the denominator. Oh, wait, that's gonna, oh, shoot. I did it. I skipped a step. All right, 5,000 times 8 times 12 cubed divided by that denominator. There we go. 0.346 inches. So this distance that we just calculated, that would be the distance that if we had our beam and we put 5,000 pounds on it, however far my finger moved right here, that is this number. Because this Y max, and we can go look at our chart over here. It's, well, not that one, that one. It shows Y max existing at the very end of the beam, which makes sense for a cantilever beam with a point load on the end of it. The maximum deflection should be at the very end of the beam. And so that's what this number is telling me. Now, if I wanted to know the deflection somewhere else, like maybe over here, I couldn't just put a different L value in here. This L is the length of the beam where the point load ends at. So if I want to know the deflection somewhere else, I need to use the equation of the elastic curve, this more complicated one where I can put in different values for X. So X is, you know, measured from the wall, X equals 0, over to some point, wherever I want to know the deflection. Just for doing it, let's build this in MathCAD. Let me put MathCAD on your screen so you can see it. Here we go. Somewhere in there. And make it a little bigger. All right. We have to put our variables in. P was 5,000 pounds, or 5 kips, whichever. L was 8 feet. E was 29 times 10 to the 6th psi. Oh, didn't want to erase it. And I, 144 inches to the 4th. PLEI, that's all the ones that we need. Let's make X go from 0 feet to, let's go by 1 inch and then go over to 8 feet. Skipped out of the thing. So we're going to go 1 inch, 2 inch, 3 inch, all the way up to 8 feet. Let's see our equation. So this is the equation for the point load. Y point load. Y of x, so it is a function of x, equals, technically it's negative, so we'll put our negative sign in there, P times L cubed over 3 times E times I. Okay? Now we could, oh wait, but that's the maximum one. Hold on. What am I doing? We want the equation of the elastic curve. The equation of the elastic curve, I don't remember. I'll have to get my thing up here and see it. So it is, y of x is p, not negative, or at least not right here, over 6 times e times I. I guess I could have finished that one out and it would have at least verified that our 0.346 was right. So this is 6 ei in the denominator times x cubed minus, there's the negative, oh, but we want it over here, there's the negative sign, 3 times L times x squared. Okay, I think that's right. Now we can verify if we were correct. So y point load at 8 feet equals, but in inches. There's the number we just calculated. But the other thing we can do here, now that it's a function of x, and we have x ranging from 0 feet to 8 feet, counting by 1 inch, is we can plot that, and we can get a shape for the whole beam. So let's insert a plot. Y of, what did I call it? Y underscore point underscore load of x with units of inches. Let's put those in inches. And then x axis is just x in inches also. And let's make it a little longer. All right, so that stays on your screen. So there's the shape of the beam as it deflects. And it does correspond with the 0.346 maximum deflection that we had at the end of the beam right here. And so you can kind of get an idea. Now, this is just a single point load on a cantilever beam. What we didn't include was, the beam's own weight. So let's go back over here and see if we can include that. So looking at our beam name, it's a S10. So the 10 refers to, if this is our beam, it refers to this distance here. How deep, tall is the beam? It's called depth in the charts. So this distance right here would be 10 inches. The 35 refers to, if I took a 1 foot section of this beam, that little section would weigh 35 pounds. So that 35 is just like we had a distributed load all the way across the beam. And it was 35 pounds per foot. So we have a case that is exactly that in our charts. Let's see if I can find them. Right here. Case 2 is a cantilever beam with a distributed load all the way across the beam. And here's the maximum deflection. We could do that, but let's just go straight into doing the equation of the elastic curve and plot it on this same plot that we just made. So it's a little bit more complicated equation. You know what? Actually, let's do the one by hand with the maximum deflection first, because there's one thing I want to point out. Let's do that one first, and then we'll plot it. I lost the pen I was writing with. There it is. All right, so this is for this beam's self-weight. Y max, also at the end of the beam, equals negative, because it's going down, W is the distributed load that would be spread across the whole beam, so that's the 35 pounds per foot. L to the fourth over 8 EI. So like I said, W is 35 pounds per foot. And here's where I wanted to just point out and make sure that we did right. Because MathCAD, it would just do it without us even realizing it. So we've been converting feet to inches quite a bit in a lot of different problems, and we just multiply times 12 is really all we do. But this is pounds per foot. So you do have to be careful, and this is one reason to write your units out carefully. To cancel out these feet, I need feet in the numerator of my conversion factor, which makes me divide by 12. So make sure you don't just automatically go multiply times 12 because you need to convert something with feet in it. And here you need to divide by 12. L is 8 feet. Convert that over and raise that whole thing to the fourth power. And then 8 E is the same material, so 29 times 10 to the 6 psi. And I is the same beam, so 147 inches to the fourth. So if we solve this, we'll get some pretty small number. 8 times 29 million times 147, that's in my denominator. 35 divided by 12 times 8 times 12 to the fourth divided by my denominator. Tiny number. 7.26 times 10 to the negative third. I don't know if that's right. Maybe it is. No, maybe it is. All right. Small number either way. We'll check it in MathCAD and see. But I do expect it to be a small number. This whole beam, 35 pounds, 8 feet, or this is pounds per foot, 8 feet, that's under 300 pounds, 280 pounds. So the whole beam does not weigh much compared to the 5,000 pounds. I've got the 5,000 pounds concentrated at the very end of the beam, so that's the worst place to put the load on a cantilever beam. And the 35 pounds per foot is spread over the entire beam. So I don't expect a large amount of deflection there. So let's put this in MathCAD and see what it tells us. All right, like I said, I was just going to put the equation of the elastic curve in. This will be y for the weight. And it's a function of x. I need to see the equation though. Let's see. So this equation right here is what we're putting in. All right, so it is negative W over 24 times E times I. That whole thing times x to the fourth. So that would be the position from the wall over to wherever I'm trying to calculate my deflection here. Minus 4 times L times x cubed. Oh, shoot. There we go. Plus 6 times L squared times x squared. I think that's it. Oh, I haven't defined W, so let's go up here and put in W. W is 35 pounds per foot. I don't like it overlapping. Let's put it over here. There we go. So it's happy now. Let's add that to our graph. Y, the weight, not parentheses though, as a function of x in units of inches. And there it is. It's that little black line that you can kind of see bending slightly. If you look at the horizontal axis here, there's a tiny, tiny little bit of deflection. So it is affecting the beam a little bit, but not that much. So how do you take that into account? What if it was bending the beam a whole lot? How do you take that into account? What you do is there is a concept called superposition. And it doesn't exist just in beam deflection. It exists in electrical circuits and all sorts of different mechanisms and beams. And the idea for superposition is that you can take the individual effects of loads and add all of those individual effects together to get the total effect on the system. So in this case, we can take the individual effect of the point load and add it to the individual effect of the beam's self-weight, and that sum would be the total deflection. Now in this case, the self-weight deflection is really small, so it doesn't make a big difference, but if you do want to include that, or if you're told to include the beam's self-weight, then you just add them together. So if we go back to MathCAD, you would quite literally have an equation y total as a function of x is equal to y point load plus y from the weight. And then we could add it in. And now it may move my axes for, you know, they're not on 0, but here's where they would have been, but it's going to snap down to negative 0.005, so I didn't want it to do that, but it's what it did. So there's that top line, not the axis line, but the top line here is the beam self-weight. The blue line is the deflection from the point load, and then the red line is basically those two equations added together to get the total deflection of the beam. And so that's what superposition is. You're taking two individual load cases in this situation where you have a beam with loads on it, and you isolate them, look at them one at a time, and then add those results together to get the total effect. All right. So what happens? So that's fine. That actually is not too bad. But we took examples exactly like they're written here. There's nothing different about what we did. We did a cantilever beam with a point load in the middle of it, or on the end of it, not the middle. We did a cantilever beam with a distributed load all the way across the thing, an evenly distributed load all the way across it. What if we had something that's not one of those cases? So let's do one where it's not. Let's do a cantilever beam still. In fact, let's do one that's very similar to what we just had, but we make it longer. So let's set this same thing up, but let's just make the beam longer. So instead of the point load being at the end of the beam, it's going to be, you know, somewhere over here. But let's use the same 5,000 pounds. And let's make the beam, or the point load, 8 feet from the wall, just like it was before. Whoops. And let's make this extension that we added on, let's make it 4 feet. And now we don't have the exact same scenario that we just used. It's a little bit different. So this does not perfectly match case 1 from our chart, because case 1 in our chart has the point load at the very end of the beam, and the beam ends at that point. But we have the point load and then there's more beam. So it's not exactly like case 1, but it's pretty close. So we can take and start with what we already had, a point load at the end of an 8-foot long beam, a 5,000 pound point load. Let's say it's the same beam. I didn't specifically say that, but let's say that it is. So now it's the exact same beam, just longer, 4 feet longer. So what I would expect is that, got the beam, I'm going to cause it to deflect. From here to here, where I'm deflecting at, that is exactly the one we just did. The only difference is that there's more to the beam. There's some more deflection over here. So I just need to figure out how to take that extra bit of deflection into account. So here's what I'm going to do. Let's draw us a little diagram down here of what's going on. So here's the original beam. I'm going to draw it as just a dotted line where the beam originally sits without any load on it. All right, so there's the original location for the beam. So it's sitting right there. And then we put 5,000 pounds on it, and we know from our MathCAD simulation roughly what it's going to look like when it bends. You know, the blue line here. I'm going to attempt to draw that, something like that anyway. Say that that's it. Something like that. So now we've got, I don't know how close this will actually match up. Yeah, it doesn't exactly match up the exact same way. It's not far off though. It's pretty close. So that, we just need to know what's going on here. So we know this deflection. So if I were to mark it out, this distance is this one, 0.346 inches. But the beam is longer. There's more to the beam. So you have to think about what is going on with the beam past here. So right here, it's not bending. It's angled downward, but this is straight. There's nothing to cause that to bend. So it's just taken off in a straight line. Wherever I left, it's kind of like you shot it out of a cannon or something, and there's no drag or gravity or anything. It's just going in a straight line, like this. Let's see if I can get it lined up with the end of the beam, something like that. So that part's straight, that part's curved, and you know, if we did it anywhere near right, then it would kind of, yeah, I mean, that lines up pretty good. We got a little bit of a mismatch right there, but pretty good on what it's doing. Now, there is one thing that's different from what is going on in the real world. So in the real world, when I bend this beam down, notice I drew, well, let's actually draw it the right way. Let's line up our beam here. All right, so that's pretty close. I drew the end of the beam landing right there. But when I take the actual beam and bend it, notice it ends up a good bit shorter than that because it's sweeping through an arc, right? And it's pulling it in as it goes around this curve here. We're ignoring that effect because we have really, really tiny deflections generally. If you have large deflections, then you probably have flexural stress problems. So these deflections are actually really small. So this whole thing is probably a lot more in scale. You know, if this is 12 feet long, it's probably more like that, you know. And there's no real discernible distance that it comes in when you do it. I'm exaggerating it when I draw it like this. It's probably way more like that. So we're ignoring the fact that that beam end actually moves in if you were to really bend it in that shape. If you really bend it in that shape, you have probably yielded it, or you've probably not done what the beam was intended to do. So we know this much, right? This is the total deflection, this thing. Now, we're ignoring the self-weight in this version of the problem. We're just thinking of the 5,000. When we did the self-weight, you know, it didn't really make much difference at all. It made a difference. You can zoom in and see a little bit of a difference, but it wasn't a large difference. So we're ignoring the self-weight. And so this Y total is this plus this. So if I just figure out this much, 0.346 plus this equals the total deflection. So this one is a triangle, assuming we ignore the fact that it actually sweeps through an arc and, you know, pulls in, and this point is really up here somewhere because we're not really bending it that far. And this side is 4 feet. So if I have a side and an angle, then I can calculate another side just with trig. So to get this angle, we have an equation, and it is not there, there. So case 1, a point load at the end or at the length L for a cantilever beam, slope at the end. So this would be slope at the end of the beam drawn in the picture. So the beam drawn in the picture is right here. It ends right here. You know, this part is not part of the beam in that picture on case 1. So if I do the equation, it's PL, or negative, PL squared over 2EI, that will give me this slope right here. So this theta is negative PL squared over 2EI. And that came from the same chart that the other equations, these equations came from. And it's just the slope at the end of the beam. So you do have to be careful. Negative, so this is theta equals negative P is 5,000 pounds. That's the only force we're dealing with. Times this L is the L that matches this L in our chart. And that L is shown from the wall to the point load. The wall to the point load is 8 feet. This is going to make units of pounds, inches squared up here. E is 29 million PSI. I is 147 inches to the fourth. So I end up with pound inches square in the denominator. So I have no units. This thing actually comes out in radians when I calculate this PL squared over 2EI. That'll give me a radian number. And the number will be 2 times 29 million times 147. So there's my denominator. 5,000 times 8 times 12 squared divided by the denominator is a pretty small number, 5.4. We'll just leave it at that, times negative 3. 10 to the negative 3. Radians. Now, I can either take that radian measure and just treat this, it is a right triangle the way I've drawn it. So right angle, and I can just use a tangent to figure out this side. Y2. So that's totally legitimate way to do it. Since we are talking about very small angles, then you can actually simplify it a little bit and just say y2 is pretty much equal to just the 4 feet here. So whatever this L2 distance is times theta. 5.4 times 10 to the negative third. So you can just multiply 4 times theta, or L2 times theta, and that's pretty much the same thing as doing the tangent and figuring out this side. Because as long as this is a small measure of radians, which it is. 4 times, well, let's see, 5.4 times, well, let's just do 0.0054 times 4. Oh, feet, so times 12. 0.2592. So if I wanted it in inches. So it's approximately equal to 0.259 inches. So then I can take those two, the 0.346 from case 1 directly, and the 0.25, whoa, that wasn't dry. The 0.259 from some information from case 1, from the fact that we took the end of the beam, the slope at the end of the beam from case 1, and figured out this triangle right here. So we'd add those two, 0.259, 0.346, and that would give us the total deflection at the end of the beam. Okay. Another one that you might run across that's not in the beam. Well, let's just look at our chart and look through some of them that have special conditions on them. So these first two are pretty standard. We just use those. This one is very similar, except there's a concentrated moment instead of a point load or a distributed load, and so the equations look similar. Here we have a simply supported beam with a point load directly in the center of it. It does give a qualifier on the equation of the elastic curve. Basically, this equation is only good for half of the beam. And you can imagine, hopefully, that if you had a beam with a point load in the middle of it, that each half is basically a mirror image of the other half. So you really only need half the equation for determining the deflection anywhere in that beam. This is maybe the most complicated one. It is a simply supported beam with a point load, but the point load's not in the middle. So there are some special qualifiers. For instance, this equation of the elastic curve, it only works in this section over here where x is less than a. So if you wanted this other section, you don't have any equation of the elastic curve for that section. You do have at x equals a, you have that equation, but you don't have it from the point load to the short end of the beam. You don't have that one, at least not in this chart. You have two different slopes at the end of the beam, so you can kind of see, they don't have them labeled on here, but the slopes are going up on one end and up on the other, and they're a little bit different angle. You can see that there's a times b in this one and a times a in the one beneath it. Here's the maximum deflection. So this one has to tell you where that exists. So it exists at this location, square root of L squared minus b squared over 3. So somewhere in here. In this equation, you have to have the a variable larger than the b. So you might be in the situation where you have to mirror image this one. So a always has to be the larger of these two distances when you're dealing with this offset point load. Even if p is further to the left, that just means that the dimension on the left side of the point load p has to be labeled b for these equations to work, and the dimension on the right hand side would be labeled as a, so it would be the mirror image. This one's pretty standard. This is a distributed load across the entire thing. This one is relatively standard. It does have one kind of tricky part. This is a concentrated moment around one end of the beam, and they specify that the maximum location for the deflection is at L over square root of 3 measured from, in this case, what they have as point A. But you have to not think of these as left and right. You have to make the landmarks the loads themselves. So in here, this distance to the maximum deflection is measured from the end that does not have the concentrated moment. So if you had a beam like this, but the concentrated moment was at this end A, then this equation L over square root of 3 would be measuring from point B over to that location. So you have to do a lot of little mental, or you could like physically draw it out and reverse everything, or mentally mirror image things when your moment's on the other end, or when your point load is shifted over to the left instead of over to the right. So you do have to be careful that you're following the diagrams that the reference is showing and the variables that they have in those diagrams and using them the way that they intend for you to. Let's do a couple of other examples that kind of combine things together but are harder to just figure out. One of them actually would include a concentrated moment. Well, it would eventually include that. It's going to start with a distributed load. So let's have a simply supported beam, sort of. So let's put one of the supports not at the end, though. We'll put the other support at the end. And then let's just put a distributed load on this little, oh wait, you can't see. Put a distributed load on the overhang here. All right, so we don't have a case that's anything like this. We don't have any that combine simply supported with cantilever, but that's what we have here. So our job is to figure out how do we convert this into something that does match one of these cases for the simply supported beams. So I don't know a way to do any of these three here, but this one's not that far off. So what we're going to use this case 7 mirrored to create this effect. In fact, let's put some numbers on it and actually calculate the thing. So let's say that this point load, or not point load, this distributed load is 3 kips per foot. And then let's put some dimensions on here. Make it 4 feet. Let's just use our 4 and 8 again. 8 feet there. And we want to find the maximum deflection in this beam, or in between the supports anyway. It could be that the point load, or I keep calling it point load, the distributed load actually causes this end to bend down more than the middle bends up, but we're going to say the maximum deflection between the supports. So what we think is happening is this part is basically behaving like case 2, just mirrored, right? It's a cantilever section with a distributed load across it. So we think this part is more or less doing something like that. And then this pulling down, I don't know if I'll be able to hold all of this, but pulling down over here, and this thing is going to make this part do something like that. And then there's that Y max that we want to find. But we don't have any cases that look like that. So what we can do is we can take this distributed load, lump it into a point load. So 3 kips per foot over spanning 4 feet, 12 kips. and then take this point load and convert it to a moment here. So this moment would be 12 kips times 2 feet, 24 kip feet. And the 24 is 12 times this distance would be 2. So now I have, it's not the same exactly, but I have case 7 just mirrored because they have the concentrated moment on the right hand side. I've got the concentrated moment on the left hand side, but it's the same thing. I have a concentrated moment at the end of a beam. You might, if you've noticed and looked at these things really closely, you might see that, see if I can get it to zoom in for us. You might see that they sometimes show a roller and a pin. You don't have to worry about roller and pin as far as these go. We're just basically treating them all as pins. They do show a roller and pin so that you don't have a statically indeterminate beam. And it would be possible in the real world to actually lift the roller off the ground if there was literally something rolling on the ground. You could put a load on it that would have caused it to lift up. But if you ever end up with that in your mind, don't worry. I actually just drew 2 pins over here, even though that would be statically indeterminate. So you can move the pin here and the roller here and the roller here and the pin, whichever way you need them to in the diagrams to make them work to match up what you actually need. So now I have case 7. And it has an equation for y max. It says y max is, I guess I'll show it to you. Right here, ml squared over 9 square root of 3 EI. So y max is ml squared over 9 square root of 3 EI. Let's just use that same beam so we don't have to go look up more I's and all that kind of stuff. So it's the same, what was it, S10 by 35 beam that we've been using. Same material with the 29 million PSI for the modulus of elasticity. M, 24 kip feet. So I'm going to put 24,000 foot-pounds. I'm going to convert that to inch-pounds. 12 inches per foot. L, this L, we got to look at what L comes from over here, and it says L is labeled as the distance between A and B, the pin and the roller. Now I just drew 2 pins, but it's this 8 feet. Not the entire length of the beam. And it's squared. So I'm going to square it and its conversion factor. 9 square root of 3. E, we said it was that 29 million. I, we said it was the same beam that we've been using. It was 147, right? Yes. And that should give us the maximum deflection. All right, 9 times square root of 3 times 29 million times 147. There's our denominator. 24,000 times 12 times 8 times 12 squared divided by the denominator. Not a lot. 0.04 inches. Now, if we wanted to know where this 0.04 inch deflection occurs, we have to look at this diagram that says it occurs L over square root of 3 measured from the end opposite of the concentrated moment. So if we were to go over from the end up. So concentrated moments over here. The other end we're going to measure from here over to our location for our maximum deflection. That distance is L over square root of 3, which for us is this L, 8 times 12, 96 inches, divided by square root of 3, 55.4 inches. But it's measured from over here, not from this end. All right, so that's another one that how do you deal with this distributed load that's cantilevered off of a simply supported beam? How do you deal with that? This is one way you might deal with it. Let's do one other one, because this one's, to me, even harder to, it's easy to do, but it's harder to visualize the first time. So this one's a cantilever beam. Whoa, draw on the thing. All right, cantilever beam, and it's going to have a distributed load. Now, if the distributed load was right here, for instance, on the wall out to some point, that is basically the one we just did earlier. Trying to get it up here. Basically this, except with case 2 equations. So you have the distributed load from here out to wherever it ends, and then you do this thing to get to the rest of the beam. So that's not too bad. But what if it's over here? You know, that's a different thing. So what if you have your distributed load you might be tempted to do what we just did right here and lump it into a concentrated force, and then go do this thing. Put a concentrated force, you got two sides of the beam, do the little triangle, and you've calculated. And that would get close, but it wouldn't be correct. It would just be kind of close. Because all of the space past, whoops, off the screen, all the space past the point load, or in this case, if you lumped this distributed load, it doesn't actually bend, it just carries on at a constant angle. But the distributed load is causing this whole section to curve. So you'd be off a little bit. You'd underestimate the deflection at the end of this beam if you created this as a lumped load and did this process. So a better process would be to use superposition to combine two loads together to create this effect. So there's one, here's the other. And both of these have to be cases that you can deal with. So they have to be something that you have equations for. So you've only got one equation on cantilever beams that has to do with distributed loads, and it's this one. So do that one first. Put a distributed load all the way across the beam. So this will definitely overestimate the deflection because you've got distributed load in this section where you didn't actually have any in the original setup. So this will overdo it. And then you add to it this. And these are going in the opposite direction. All of these are the same. So if this is W, then this is W, and this is W. But these sections, oh, and this is basically case 2. It's upside down, so it's everything's bending upwards. But it's case 2 where you do this exact same thing, right? You run the distributed load out, calculate the deflection at the end of the case 2, calculate the slope at the end of case 2, and then calculate your add-on, you know, for this section of the beam. But what it also does is right, you know, here, which should have lined up with that point. It looks like I kind of missed. I've got W going down for X number of feet. I've got the same exact W going up. So these sections cancel each other out when you add them together. So that one is harder to be intuitive about how to figure out how to deal with this. Most people's intuition is going to be put a lumped load in the center of that and do case 1 just like we did the very first example as. And that will get close. So as an estimation, that's probably simpler to do, but this would be a more correct way to do it so that you actually get the effect of this beam continuing to curl down under the distributed load, and then you nullify or negate the fact that there's no distributed load in this section. All right, what we're going to do next time is more beam deflection. We'll probably work some more examples too, but the main point of next time will be how do you even get these equations to begin with. So these equations, the maximum one and the slope, those are just coming from this special cases of this equation of the elastic curve. So instance, you take the derivative and set it equal to 0, you can find the maximum deflection. But where does the equation of the elastic curve come from? And that's what we'll do next time. We'll figure out where the equation of the elastic curve comes from, and then we'll work a couple more examples, and that should probably get us all of beam deflection done. And that might actually be our last beam topic. We might be done with beams now, and then we can move on to the last third of the quarter, which is last third of the course, which is all the other things, mainly torsion, but some other special cases, some stress concentrations, things like that. So that's what we'll do next time. I will see you on Wednesday.